right, I was going to finish up just a few slides on controlled release membranes, and then start talking about a very different problem, and that is water and salt transport in desalination membranes. And so the last couple of controlled release concepts we'll talk about are one involving swelling controlled release systems, and a lot of the systems that we've talked about so far depend upon the active agent or active ingredient, what we call AI, being soluble in the polymer and also soluble in the medium surrounding the polymer into which the active ingredient is being released. There are strategies for releasing components that are insoluble in the environment in which they're going to be released. For example, very hydrophobic drugs being released into the body. And one of the approaches to release a compound that wouldn't ordinarily want to simply diffuse out of a membrane on its own is to incorporate it into a polymer that will swell in water or swell in the environment in which it's to be used, and the active agent can then diffuse out of that matrix once it's swollen and plasticizes. As a polymer, for example, absorbs water or solvent, it will swell. This will increase the chain motion and increases diffusion of all components. When the diffusion of the solvent and water is rate controlling, then you get release kinetics that follows standard inverse square root time. Basically, they follow the rate at which water is imbibed into the system, or solvents imbibed into the system. There is another opposite extreme that you can see, and that is when diffusion is not the rate controlling step in transport. So we have talked about systems so far where the motion of a small molecule or a penetrant in a polymer is gated by the molecular motions of the polymer chains and by random diffusion. However, there are situations where the rate at which a compound can be released depends upon how rapidly, in this case, the solvent can penetrate a polymer, and in some cases this is controlled by the rate of relaxation of the polymer chains as they swell. We'll give an example of that in just a moment to make it clearer. So this is talking about the simplest case where one would have diffusion of a solvent into a device, and if that follows Fick's law, then the rate at which the device uptakes the solvent is follows square root of time kinetics, and as the system swells, then the active agent can be released. And so this shows basically the Fickian release profiles that we've come to see previously, and the diffusion of an active agent out of such a device will follow closely the rate at which water or solvent is imbibed. The other case that's of interest is so-called case 2 diffusion. Case 1 diffusion is what's normally referred to as Fickian diffusion. Case 2 diffusion is a term that's coined by Turner Alfred many years ago to describe situations where diffusion coefficients can depend strongly on both concentration and time, and the rate of solvent uptake is largely determined by the rate of swelling and relaxation of the polymer chain. So one of the underlying assumptions in the standard model of diffusion is that as a polymer absorbs a solvent, that the polymer can swell to accommodate that penetrant in the same way that if you mix two solutions together, often very closely volume additivity is observed. However, that doesn't have to be the case. The rate at which the material or polymer can absorb solvent can be dictated by the rate at which the polymer chains can relax to allow that swelling to occur. And in these cases, the solvent is typically confined to a very narrow region of the material, and it moves in more or less a front through the material. You can see examples of this in systems like polystyrene with organic solvents like cyclohexane. If you take a film of polystyrene and put it in something like cyclohexane, the rate at which it uptakes that penetrant is not dictated by the diffusion coefficient of cyclohexane and polystyrene. It's dictated by the rate at which the polymer chains can uncoil and relax from one another to allow allow the solvent to be absorbed, and that doesn't necessarily follow Fickian kinetics. And in an ideal case, you'll just have a swollen matrix behind a zone where the concentration of solvent changes very rapidly, and this swollen matrix zone will propagate almost linearly in time, in the simplest case, linearly in time throughout the sample. And this can give rise to release kinetics that are linear in time. So case 2 diffusion is one where this exponent on T is equal to 1. Fickian diffusion is the case where you get simply T to the 1/2 release kinetics. And there are cases where you can have a mixture of diffusion and swelling controlled release. And in this region, N will be between 1/2 and 1. And this is often called anomalous diffusion in the literature. Here's an example from one of my colleagues, Professor Peppas, and studying the release of theophylline from a polyhydroxyethyl methacrylate sheet or slab. And so HEMA will absorb some water, and that rate of absorption of water then controls how rapidly the drug can be released from this device. There's some more explanation from Baker's book given here. Another type of device that is used to release compounds that wouldn't normally be readily released into an environment in which they're not soluble is so-called osmotic pumps. This is it's called a Rose-Nelson pump after the people who invented it. It's been around quite some time. And the idea in this particular case is there is a drug in one end of this device. There's an opening for it to come out. And this would be a case where the drug would not normally be soluble in the environment in which it's going to be released. There's an elastic diaphragm, and behind it a chamber containing an osmotic agent, which is often a salt or sugar, and then a membrane that is permeable to water. And as water contacts this chamber with salt next to it, there sets up a very large gradient in chemical potential of water and so-called osmotic pressure of water that favors water diffusing into the salt. And as water diffuses into the salt, then it swells, it pushes against this membrane, and then the drug is released through the device. And so if the rate of drug release in this case is controlled by the rate at which water permeates across the membrane on the back side of this device. This is some example of the kinds of agents that are used for that osmotic release and the sorts of osmotic pressure or chemical potential gradients that can be established. The rate of release in such a device depends upon the cross-sectional area available for water transport, the permeability of water through the water permeable membrane on the back of the device, the thickness of that layer, and then the difference in the osmotic pressure of the core versus the surroundings. And as we saw in just a slide or two ago, this difference in osmotic pressure, the osmotic pressure of the surroundings is fairly low. This difference in osmotic pressure can be that of the core osmotic agent, and that can be hundreds of atmospheres in some cases, and so that provides a strong driving force for transport of water across the water permeable membrane that then ejects the drug and out of the core of the device, and this is the concentration of drug in that device. This will be the last I'll talk about controlled delivery devices, and I'm going to turn now to another topic, which is desalination. This is practiced by membranes in so-called reverse osmosis, as well as other techniques. And just by way of introduction, I'll show a little bit about the background information on the importance of water purification. We have a growing crisis around the world, and that is a lack of access to clean water, and it's growing more severe. This is showing water stress areas in 1995 and projected water stress areas in 2025. And what it's showing is that we're withdrawing water in many cases faster than it's able to be recharged in the in aquifers and wells and things like that. So we're gradually depleting the groundwater of fresh water. Today, there's more than 1 billion people around the world that don't have access to clean water, and nearly half the Earth's population lives in a water-stressed area. And this has an enormous cost in terms of medical problems that arise from drinking contaminated water. This problem's been with us for a while. I love this quote by John Kennedy that really launched the formation of the modern desalination membrane industry. And so there was a recognition in the early 60s that if one could desalinate water, that this could not only solve meet human needs, but could also be of great importance in helping avoid strife and political problems in a lot of places around the world where water shortages are an issue. The National Research Council, which is basically the arm of the government that advises Congress on science and technology, has set the agenda that is shown here to develop new supply enhancing technology and reducing the cost of existing technologies like desalination. We were in a historic drought some years ago in Texas, and these come and go, but this is one from about 2012 and shows an example of how dry it can be. The darker these colors are, the more intense is the water shortage. And the thing that I think is of interest is you would suspect that in places like the Southwest and the West that there would be water shortages, but there are droughts in many places across the U.S. and this changes some with time. But the idea that this is only a problem in the U.S. in the West and Southwest is no longer true. And so looking for new sources of water and ways to purify dirty water is a major need. And it's not that we have a shortage of water, we have an abundance actually of water. The problem is the vast majority of it is tied up in the ocean, where it's too saline for human use and many other beneficial uses. Of the small amount of water that is fresh water, a large fraction of that is tied up in glaciers that are relatively inaccessible. And of the surface water that's not frozen, a fair amount of that is tied up in ice and snow in areas that are again not where a lot of people don't live. And so there's actually of the water that is that's on the earth, only a small fraction of it is easily accessible fresh water. It's been known since antiquity that you can desalinate, for example, seawater by vaporizing it and then cooling the vapor. The water evaporates, but not the salt. The issue is that this comes at an absolutely enormous cost in energy. I'll show you some more numbers to be able to compare that. With some engineering involving energy recovery between this heating and cooling step, these numbers can be brought down significantly. And in fact, many of the modern thermal desalination systems are based around this sort of technology. I was in Qatar a couple of weeks ago, and virtually all of their water is desalinated. They desalinate the Persian Gulf to get their drinking water, and they do it essentially all by thermal desalination. And the reason for that is that they're sitting on something like a third or more of the world's known natural gas reserves. And if energy is free, you can afford to do this in an energy intensive fashion. But if you look at this number and then compare it to numbers that are available for reverse osmosis, this begins to tell you why technology like reverse osmosis has now come to dominate this business of desalination in parts of the world where energy isn't free. The way that this process works in the simplest case is that saline water, it can be run through a pretreatment or filtration process to remove particulates, control biological activity, and so forth, and then pressurized to high pressure. And today, for seawater desalination, that'd be about 800 psi, and put through a membrane that allows water to permeate across it, but very little salt. And so you produce two streams, one that has the desalinated water and one that has a concentrated brine that has to be discharged. A lot of the energy in this process, well, in fact, pretty much all of it is in this pumping process to raise the pressure of the water to provide the driving force for mass transport. And there have now been developed mechanical systems called pressure exchangers that allows one to recover a lot of this energy that would be in the brine discharge that's at high pressure, and exchange that with feed water, and this contributes to high energy efficiency in these devices. This is an example of the picture from inside the Ashkelon desalination plant on the Mediterranean Sea. This is in Israel, just north of the Gaza Strip. The membranes are contained in these tubes. They're basically flat sheet membranes that are rolled up in so-called spiral wound modules. This particular plant has 1.5 million square meters of membrane area. I don't quite know how to put that into perspective, but it's a lot of membrane area, and supplies about 13% of Israel's water needs. Today, it's been dwarfed by plants that are more than twice this size that are built further up along the Mediterranean coast, and now Israel gets more than half their water by desalting the Mediterranean Sea. And this has caused remarkable changes in the way people live there. Farmers no longer have to worry about whether it's going to rain or not, and whether their crops will grow, for example. There is a very strong connection between water and energy. We need enormous amounts of energy to purify water, and it turns out that we use an awful lot of water in order to make energy. As an example of that, this is a chart of the water use in the U.S., and about half of the water that we withdraw from lakes and the ocean and rivers and so forth is used for thermoelectric power stations and as cooling water. Now, a lot of that water is returned back to the environment that it was taken from. However, it is always filtered and cleaned before it's used in that application. And so this just emphasizes the importance of, or important connection between clean water and energy generation. There is a strong relationship between economic growth and the global water use, and it's estimated that every $1 million of gross domestic product increase requires about 22,000 cubic meters per year of water. So you can imagine, as economic activity picks up, you need more water for electricity to run factories and so forth, and this drives the need for more water. Another application that has been considered is actually to use salinity gradients to generate electricity, and this is in the field of forward osmosis, or so-called pressure retarded osmosis. The idea here is that you can take a membrane that is selectively permeable to water and not salt, and on one side of the membrane put brackish water or saline water, and on the other side flow fresh water. The natural gradient for transport in this case is for the fresh water to go across the membrane to dilute the salt out of the saltwater side of this membrane, and you can use that to raise a pressure head. You can rather than simply diluting the water and expanding its volume and keeping it at the same pressure, you can actually use this phenomena to increase the pressure of the salt water, and then use that to drive a turbine and generate electricity. There have been demonstration projects of this type in a number of places. This one is by Statkraft, which is a Norwegian power plant. Here's some more examples of this relationship between water and energy. Because we use so much of our fresh water to generate electricity, when we have a shortage of fresh water, it impacts our ability to generate power in thermoelectric power plants. And during the drought in the 2011-2012 time period, power plants actually have to slow down generation of electricity because there's not enough water to run them. That's a problem right here in Texas and throughout the West at that time. It's also driven Texas to become a leader in so-called direct potable reuse, or DPR, to take municipal wastewater and turn it directly back into drinking water through advanced treatment technology and filtration. So there's a number of ways that polymer membranes are used to address water and energy needs. Some of them are well developed now. Reverse osmosis, nanofiltration is a cousin to reverse osmosis. We've talked a little bit about electrodialysis already, and other techniques that are up and coming. There are ways to use membranes to generate energy. So-called blue energy is energy from the ocean, and we talked about the osmotic power one just a moment ago, and I'll share with you a bit later work on reverse electrodialysis. There's also enormous amounts of energy that is being gained today in buildings using membranes through energy recovery ventilation. And so here the issue is that you can imagine on a nice warm day in Texas in July that we have the air conditioners running full blast, and they're taking warm, humid air in from the outside, and cooling it, condensing water out of it, circulating it through the buildings, and then there's an exhaust on that system. And some of that air is exhausted to the outside. And what's being done now in more and more building ventilation systems, and in fact in some home systems, is to take the exhaust air, which is cool and low humidity, and contact it across a membrane that's very permeable to water with the air that's coming into the building from outside, and to use that to draw some of the water out of the hot air that's going to go to the air conditioning system, and that lowers the demand for having to condense water in the system, which is the energy hog in air conditioning. It's really the condensation. And all of these technologies, or many of them, rely on polymer membranes to control either water and or salt transport. And so I'll show you an example of a modern desalination membrane. This is the cross-sectional picture of a reverse osmosis membrane that's used for desalinating water. And the way these are made is they start with a microporous polymer support, typically polysulfone. It's used for essentially mechanical support. And then there is polymerized on top of this support a very thin, on the order of 100 nanometers or less, of a barrier layer that allows water to transport across this membrane, but not salt to a large extent. And it's typically made out of polyamide today. These membranes are made in continuous processes. They were first developed by John Cadott in the late 70s, and this structure and method of making desalination membranes has come to essentially to dominate the industry. And so the first step is to make this polysulfone support that's microporous. That's done in a continuous casting process, so-called phase inversion process for membrane formation. And then the pores of this membrane are saturated or filled with water that contains a low concentration, a few weight percent, of metaphenylene diamine. The top surface of the membrane then is essentially, you wipe the excess solution off of it, typically in a continuous process with an air knife, and a layer of oil or an organic phase is put on top of this membrane, and it contains a compound known as trimethyl chloride. The trimethyl chloride has almost no solubility in water. The metaphenylene diamine, while it's water soluble in the concentrations it's used, it has a bit of solubility in the oil phase as well. These aromatic amines and acyl chlorides are violently reactive with one another, and so as these two layers contact one another, metaphenylene diamine and the trimethyl chloride react almost instantaneously at that oil-water interface. And there is additional diffusion. Well, that's a pity. It's not going to, animation's not going to show. But anyway, there's a buildup of this barrier layer as the metaphenylene diamine diffuses into the growing polymer film to react with more trimethyl chloride. It's a self-limiting reaction because once this barrier layer gets to be on the order of 100 nanometers thick, the rate of diffusion of the metaphenylene diamine through that barrier layer gets to be very slow, and the reaction essentially stops. You can make these in the lab by processes that are require just a few seconds to polymerize that layer. So this is the way that desalination membranes are made, and the typical chemistry. They are formed in terms of a cross-linked structure. We talked earlier in the gas separation area about the trade-off of, let's see, I'm having troubles here. Let me see if I can get the wow. So I'm trying to get it's stuck. I'm going to turn the display off and back on and see if that will help get things going again. Okay, there we go. There's my desalination membrane growing in, and the structure of the resulting cross-linked polymer. We talked for a while about the trade-off between permeability and selectivity in gas separation membranes. This is observed ubiquitously across the spectrum of membrane filtration. This is showing one incarnation of that for desalination membranes, and it's what it's showing is that as you increase the rate at which water is transported through a given polymer, you typically lose the ability to gate how much salt comes through. And it's showing where standard seawater reverse osmosis membranes they typically have salt passage that's well under 1%, so more greater than 99% rejection. If the salt content is lower, such that the water is brackish, then brackish water RO membranes can be used. They have somewhat lower rejection, but they typically don't need as high a rejection. And there are other applications we'll talk about that have even lower rejection. These are so-called nanofiltration membranes. And this is just a reminder of the connection between the data on the previous slide and the gas separation upper bound. Wanted to talk a little bit about water and salt transport through polymers, and today focus mainly on water transport. This is one of the most interesting technical problems and somewhat counterintuitive bits of science that we'll talk about this term. And the salt transport through a desalination membrane, which is a non-porous membrane of thickness L, the steady state salt transport is governed basically by fixed law. There's a difference in salt concentration in saline solution on one side of the membrane and in the permeate or clean water side of the membrane. And that difference in salt concentration sets up a flux of salt through the membrane and drives the transport of salt through the membrane. Fixed law would have the flux being proportional to the concentration difference inside the membrane. There is a partitioning of salt between the external phase and the internal phase, or between the outside and the inside of the membrane. And one can use that partition coefficient to write the salt flux in terms of the external concentration of salt and the permeability coefficient. And this is typically the way it's described in the literature. To get the water to flow across this membrane, a hydrostatic pressure difference is imposed. And this hydrostatic pressure difference leads to a chemical potential gradient in water that we'll talk about in a moment. And that leads to a concentration gradient in water that then drives water transport by Fickian diffusion. The relationship between the internal concentration of water in the membrane and the external concentration is generally written in terms of the difference between the hydrostatic pressure difference, that is the bead pressure minus the permeate pressure, and the osmotic pressure difference, which is the osmotic pressure of the feed solution minus that of the permeate solution. And this depends very directly on salt concentration in these solutions. This pressure gradient drives the water transport. It has almost no effect on salt transport, as we'll come to see when we have a closer look at this. In both water and salt transport, we can write the permeability of water or salt as a product of a partition coefficient of either water or salt times the diffusion coefficient. This kind of concentration-driven transport of charged species like sodium and chloride ions, for example, means that the transport of ions through such a membrane is electrostatically coupled, because one of the things that is required in all solutions and membranes is to maintain electroneutrality. And so every time there is for example, a sodium ion that is transported through that membrane, there has to be a chloride that comes with it, and that electrostatic coupling between the ions keeps them moving together essentially through the material. We'll come back to this description a bit later in this discussion and talk about this a bit more. The standard expressions to describe water and salt flux are shown here. Rho 1 and V1 bar are the density of water in the membrane and the partial molar volume of water. The permeabilities are written exactly as we would have written them before in terms of a solubility or partition coefficient and a diffusion coefficient. We can also talk about the selectivity of water over salt in terms of the solubility and diffusion selectivity, exactly the same way we would have done this for gas separation. Now, typically in desalination membranes, we don't talk as much about these selectivities as we do about rejection, which is the ability of the membrane to reject salt. And we'll discuss in a little bit greater detail later this rejection coefficient, which basically is the percentage of salt that is not allowed to pass through the membrane, is intimately connected with the water to salt selectivity of the membrane, but also to operational parameters like the pressure difference and through the osmotic pressure, the salt concentration differences. This is a little more marketing about the size of the desalination membrane and membrane processes for desalination are taking a large part of this market today due to their energy efficiency relative to conventional technologies. To give you some idea about the size of this market, but I like to think about it this way. If you think about a fluid that we produce in great amounts and move around quite a bit, oil might come to mind. And so this is, at least in 2005, was the number of billion gallons of oil that we process per day. And we're desalinating 3 times that amount of water. So just to put this in some scale, now water is not as valuable most of the time as oil, so you don't see it moved around in huge super tankers, but this is happening at very large scale. So showing a top view of a desalination membrane that this one's from, now it was GE, is now Suez. And these are brackish water membranes, so they typically operate at somewhat lower pressure than seawater membranes. They're built to take salt out of low concentration salt sources, things that might be 2,000 or 3,000 parts per million salt, rather than 32,000 parts per million like seawater. These are typical sodium chloride rejections and operating fluxes. They have a very similar structure to the one that I showed you before. And if you recall how the mechanism by which these membranes are formed, it's the metaphenylene diffusing through this oil layer to react with trimethyl chloride at the oil-water interface. And that creates this irregular or nodular structure on the surface of these membranes that sometimes is attributed to to fouling of the membranes. So you have a lot of nooks and crannies where if there are particles or other contaminants in the water, they can get stuck and block membrane transport. And also there are notions in the literature that this very corrugated rough surface creates extra surface area that assists in transport. This is showing the process by which these membranes are made, and we talked about that a little bit earlier. Here are some of the applications. I won't dwell on this, but these types of membranes are used for salt removal. They're also used for removing, in some cases, organics and treating things like textile wastewater to remove color. Used to make boiler water for industrial water production, and they're used in a number of places around the world for treating municipal wastewater. Brackish water desalination is practiced widely here in Texas. So if you go to San Antonio, they have a large, going on 25 million gallons a day, brackish water desalination plant that takes saline water from an aquifer under San Antonio and desalts it for drinking water. You go up the road to the north to Waco, and they also use desalination to desalt their good fraction of their drinking water. Out in El Paso, the world's largest inland brackish water desalination plant is located, so-called K. Bailey Hutchison plant. So this is widely used for potable water production. We also use it for municipal wastewater. In Los Angeles, the water is taken largely from a freshwater underground aquifer to make drinking water in that area. And if water is removed from that aquifer but not put back into it, there is seawater intrusion into the aquifer, and it makes it gradually more saline over time. And so what's done today is there's a series of injection wells that stand between the coast and a large fraction of that aquifer. And as Los Angeles water flows into the wastewater treatment system, it goes finally through membrane filtration, desalination membranes. It's re-injected back into the aquifer to keep seawater intrusion out of the from contaminating the aquifer. There are a large number of applications in the food processing space. I won't go through all of these in detail, but there's a good collection of them in this work by Dibakar Bhattacharya and colleagues in the Membrane Handbook. We often distinguish between reverse osmosis and nanofiltration membranes. They're made by a very similar process as the one I just described to you. The nanofiltration membranes would often be referred to as slightly defective reverse osmosis membranes. In addition to having the RO membranes are strictly non-porous, dense materials, and the nanofiltration membranes can have the same chemistry, but they have a low level of tiny pores that allow some convective flow. And this reduces the salt rejection, but markedly increases the rate at which water permeates through these materials. In general, in terms of the performance of these membranes, water flux goes up with linearly with the pressure difference across the membrane, and we're going to talk today about the basic mechanism that underpins this and why this happens. The water flux goes up with pressure. The salt flux does not. It's largely independent of pressure, and as a result, the salt rejection gets better as these membranes are operated at higher and higher pressure. simply because you're putting more water through the membrane with the same amount of salt coming through it, and so the salt concentration in the permeate is going down. This is a so-called FilmTech 30 membrane. So the initial reverse osmosis membranes made by Interfacial Polymerization were made at a company called FilmTech that later became Dow FilmTech and now is Dow Water Solutions. It's the largest desalination membrane company in the world. And this was, I guess, the 30th try in making some of these membranes. As you might imagine, water flux would increase with temperature. There is some trade-off with salt rejection. And for this reason, you'll often see nowadays desalination plants, if it's seawater desalination, they're often co-located with power plants. And so the cooling water coming out of power plants is typically warm, and it's also clean. And this can be used in some cases as the input to desalination plants. And you can get much higher flux if the temperature is a bit warmer. The dependence on salt content is that as the salt content of the feed water goes up, the water flux comes down. Essentially, the more salt there is in the water at given operating condition or operating pressure, the lower the water flux will be, because the water flux depends on the delta P minus the delta pi, the osmotic pressure difference. And as water flux comes down, then salt rejection also comes down with it. These are showing some of the standard materials. Cellulose acetate is still used a bit for desalination membranes in the Middle East. It was the dominant material early on in this business, but was later replaced with the aromatic polyamides. There's a couple flavors of these. We talked about the metaphenylene diamine trimethyl chloride variants. There are also piperazine-based materials as well. This is a plot of water flux versus sodium chloride rejection, and it shows where, for example, the original cellulose triacetate was located, and other types of membranes. The cross-linked aromatic polyamides have come to dominate this business, and there's one of the most important rejection figures is this one at 99.3%, which is the minimum rejection that's required in order to take seawater and turn it into potable drinking water in a single pass. And so when membranes started to have rejection above 99.3% under seawater desalination conditions, this business really took off. So I'd like to talk about the fundamentals first of water and then later salt transport through these membranes. The way that you'll see the water and salt flux described in the literature is shown here. The water flux is taken to be proportional to the pressure difference across the membrane and also the osmotic pressure difference. That'll be the difference in salt concentration across the membrane. And this parameter A is often reported by manufacturers in the literature as a permeability or permeance to water. Salt flux is typically written in terms of concentration difference of salt across the membrane, and B is an empirical parameter that just characterizes the salt rate of salt transport across the membrane. It will be related to salt permeability and thickness. If we come back to this slide, you can see that B is the salt permeability per unit thickness of the membrane, and A is this grouping of terms that includes water permeability, thickness of the membranes, and then the density and partial molar volume of water. Salt rejection is defined as the difference between the salt concentration in the feed and the permeate. divided by that in the feed, and this can then be further related to the perm selectivity of the membrane as well as operating conditions. And so a question that I'd like to talk about over the next little while is why does a pressure difference across a membrane cause water transport? So if you think about it, you have a somewhat hydrophilic membrane and you apply a pressure difference across it. How does that drive water transport? Freddie, you got any ideas? I know, sitting there minding your own business.
Yeah. Normal pressure driven flow, but the osmotic gets so low that the pressure, the apply pressure you just overcome the difference in so low.
Yeah, so we'll look first at the case where there's no salt in the water. Just take a membrane, have water on both sides, and raise the pressure on one side. And how does that establish a concentration gradient in water that then allows water to be driven by vacuum diffusion? Let me think about it a second. This is, it's an interesting intellectual exercise that we're going to talk about. Well, let me ask the question another way. If I raise this feed pressure, what happens to the concentration gradient in the membrane? And we just saw water flux goes up as the delta P goes up. You saw that in the experimental data I showed you a few slides back. Why does that happen? So as the feed pressure goes up, water flux increases. What's happening to the concentration gradient inside that membrane? Okay, it increases. Now, does it increase by the water concentration on the feed side going up, or by the water concentration on the permeate side going down, right? There's two ways that you could increase that gradient, right? Which do you think it would be? Sorry? Okay, who agrees with JC? Yeah.
You're pushing the molecules into the surface, so it's just increased.
All right. I think that is exactly the answer that 99.9% of the people who are skilled in this art would have.
It's the purpose of
It's not wrong.
I don't remember the numbers. I remember the numbers in the purpose side was always lower to make it dry faster.
Yeah, have a look at this. I think this is one of the most remarkable sets of experimental data that you could find, because this was a controversial topic in the late 60s and early 70s, and it was work here at the University of Texas by Professor Don Paul that finally put this issue to rest. And so what's being done here, this is Rosenbaum and Cotton were at Dow. Dow was competing in the 60s and 70s to make cellulose acetate membranes. They're big into cellulose acetate. They ultimately made cellulose acetate membranes for natural gas separation, and those have gone on to dominate the worldwide market for natural gas separation membranes. Dow spun that business out many years ago, so they're not called Dow membranes anymore. Now part of Schlumberger. But they were also looking at cellulose acetate as a material for desalinating water, desalination membrane. In fact, in the early 60s, it had been a couple of graduate students at UCLA who made the first phase inversion cellulose acetate membranes that gave high flux and high salt rejection that kicked off the desalination membrane business. And so cellulose acetate was ultimately commercialized for desalination. And Rosenbaum and Cotton are doing fundamental studies here to understand how water and in related studies, salt is transported through these membranes. And so what they've done is they have taken a series of 4 membranes and stacked them together. And they clamp them into a permeation cell, put water above them, and then with a little tube coming out of the cell at the bottom to drain the water that permeates through the membranes. And then they put feed pressure at 68 atmospheres. The permeate was at atmospheric. So they put 68 atmospheres of pressure on the water that's sitting above this stack of 4 membranes. And they've let the water flux come to steady state. And then they release the pressure on the upstream side of the membrane, take the permeation cell apart and separate the membranes. So you have 4 separate membranes, and then they measure the water content in each of those membranes. And this is the water content in each of at the mid, and they report it like the midpoint of the thickness of the membrane. And then they do the experiment again, except this time the feed pressure is raised to 136 atmospheres. So it's double. And what has happened to the water concentration at the upstream or high pressure side of the membrane? Virtually nothing. What about downstream? I mean, this to me seems like magic. You raise the pressure here, and it lowers the concentration here. And that's experimental fact. I mean, this is, there's just no getting around it. And so the question then is, at a fundamental level, why is this happening? How do we understand it? And one of the keys to that came from work that was done here at the University of Texas by Don Paul and student Ebra Lima. There's a series of probably 15. Ebra Lima was an extremely productive PhD student. And if you find these papers, there's just a boatload of them. Now, the Rosenbaum and Cotton study was in 1969. And in 1971, Don Paul and the students are using the same approach to not to measure water permeation across membranes, across hydrophilic membranes, but to study organic solvent filtration across hydrophobic membranes, rubbery polymer membranes. And this has ultimately gone on today and is now a fashionable research area known as organic solvent nanofiltration. So using hydrostatic pressure to drive organic solvents through membranes as a way of separating mixtures of organics without having to boil them or to use phase transformation to do that. And so what they have done is they have followed the same procedure as Rosenbaum and Cotton. They've stacked several membranes together and then set up an experiment where, in this case, I guess it's cyclohexanone and being transported across a cross-linked rubber and membrane. And they've set the upstream pressure at 400 psi, and the permeate pressure is at ambient. And they've measured the essentially the composition profile of the organic liquid across that membrane. And what they find is that the solvent volume fraction, and these numbers are high, so these membranes swell a lot in this organic solvent, that the solvent volume fraction at the upstream face of the membrane is about equal to the solvent volume fraction you'd get if you just took that membrane and soaked it in a dish of cyclohexanone at ambient pressure. So take the membrane, just put it in a big beaker of cyclohexanone, at ambient pressure, let it absorb as much of the solvent as it wants, and then weigh it and dry it. And under 400 pounds of pressure, the concentration of solvent here is about equal to the concentration of solvent the membrane had just equilibrated at atmospheric pressure. So again, what we see is that raising the pressure on the feed side of the membrane isn't doing anything to the concentration of solvent dissolved in that membrane at the feed side. It is, however, lowering the solvent on the permeate side of the membrane. And that's what sets the gradient in concentration of solvent that drives the transport. So here's another example where you raise the pressure on the feed side and it causes the concentration of the permeate to go down on the permeate side. And so the way we will come to understand how we get to this performance equation, which is ubiquitously used to describe water transport across desalination membranes, how we get to here, starting from just fixed law diffusion of water through the membrane. And so based on the Rosenbaum and Cotton work and this work that I've shown you by Don Paul, one of the beginning points here is to understand how pressure impacts the concentration of solvent or the concentration of water dissolved in a polymer. And these are studies from Ham and colleagues from the early 60s. I have no idea why they were doing this, but they were taking samples of rubber and swelling them in organic solvents. And then with the rubber surrounded by solvent, they were pressurizing the solvent and monitoring the change in the volume of the swollen rubber, okay, as a means of monitoring whether the concentration of solvent inside the polymer increased or decreased as the pressure of the solvent went up. So you have just a sample. I think there's a picture. I don't know if I have their device, but anyways, you basically have a rubber sample in a chamber. It's completely surrounded by solvent, and then you increase the pressure on the solvent, and therefore the pressure on the rubber sample. And they're able to measure the volume of that polymer. Here it's relative to the volume of the polymer if it were just swollen at ambient pressure, in this case chlorobenzene. And and what they find is, and the pressures now are nuts relative to what we use in membranes, right? 30,000 psi. This is really, really high pressure. And what they find is that immediately after applying pressure, they do see the volume of the sample decrease. And then gradually, if they hold the sample at pressure, the volume goes up again. So what's happening here? You compress the sample a little bit, and it gradually absorbs solvent back until it comes to equilibrium. And here's the equilibrium line. And what I want you to look at is how little the volume of that sample is changing over this extraordinary pressure range. Right? Look at these numbers. This is 0.95, 0.96, so 25,000 pounds per square inch. The amount of chlorobenzene that this rubber sample has taken up has gone down by 4%. And if you think about what kind of pressure we would use in desalination, it's way over here, generously, right? And I mean, there's just no way that you have much of a change on the constant, based on the experimental data, much of a change on the concentration of the water of the high pressure water in contact with that membrane. But that's not the end of this story. First was chlorobenzene in heavier rubber, so this is trans-isoprene. Now, chlorobenzene in a different rubber, cross-linked rubber, neoprene. And again, apply the pressure, volume looks like it goes down, but then it gradually absorbs solvent again, comes to equilibrium. And now, at the end of the day, 30,000 psi, the volume of the sample has actually increased by a couple percent relative to what it was at just soaking the sample in the solvent at ambient conditions. So the concentration of solvent with pressure can go down a little bit at extremely high pressures, or it can go up a little bit, depending on the solvent and polymer. What do you think is causing that? How would you begin to analyze it? Let's say it's at thermodynamic equilibrium. How would you start to analyze this problem? Thank you. There's the chemical engineers in the room are going to set the chemical potential at the in the surrounding solvent equal to that in the membrane at thermodynamic equilibrium. And we'll take this. We'll come back to the water case as we go into this. Things with a superscript M on them are going to be in the membrane. So at thermodynamic equilibrium, the chemical potential of the water just next to the membrane surface and the chemical potential of the water inside the membrane surface are equal to one another. We'll take that as the gospel. How does pressure affect the chemical potential of a liquid? Use thermodynamics. You knew this at one point. I know you did. Remember the partial molar volume? Remember the Maxwell relations and all that jazz? Okay. In a pure liquid, the way that pressure affects chemical potential is just the molar volume. So the molar volume is essentially the change in chemical potential with pressure. And in a mixture, so if you've got say a membrane, say water dissolved in a membrane, the way that pressure affects the chemical potential of water in the membrane is called the partial molar volume. Okay? And it's going to turn out that the molar volume and partial molar volume of water, the molar volume of pure water and the partial molar volume of water inside one of these desalination membranes are essentially equal to one another. But just remind you of those definitions and the definition of the partial molar properties. Okay. So now back to the experiment that Ham and colleagues were running. So they have a membrane and surrounded by a solvent, and then they apply high pressure on the solvent and therefore on the membrane. We're going to call it the feed PF. And so the way that the chemical potential will change with pressure in the water phase is given by this expression, right? We just integrate that definition of molar volume. So the chemical potential of the water at a given pressure piece of F is equal to that at a reference pressure. That's going to be ambient, okay, just so we're clear, plus the integral of the molar volume of water integrate over this pressure range. And for all intents and purposes, we're going to treat water as being incompressible. So this molar volume is going to come out of this integral, and it's just going to be the molar volume times the pressure difference. That hydrostatic pressure is transmitted to the membrane. And so the water that's dissolved in the membrane also is exposed to this pressure, and the chemical potential of water inside the membrane increases according to the partial molar volume of water in the membrane. Now, the partial molar volume is just the analog of molar volume, but now we're talking about water dissolved in the membrane rather than water in water. And so we can equate the chemical potential of water at this interface. And in the pure water feed, we just integrate the expression on the previous page, use the reference pressure as the permeate pressure, and so this is the way the chemical potential increases in the pure water phase as the pressure here goes up. Now, in the membrane, there's two ways that the water chemical potential can change. One is it can change as the pressure changes according to the partial molar volume of water. But you can also change the chemical potential of water inside that membrane by changing its concentration. And the activity of water term here is essentially how much the chemical potential changes as the concentration of water inside the membrane changes. And so now imagine what's gonna happen as we raise the feed pressure here. So as we raise the feed pressure, what's happening to the chemical potential in the water? It's increasing, just linearly proportional to whatever that feed pressure is. What's happening to the chemical potential of the water just at the surface, dissolved in the surface of this membrane that's also exposed to that pressure? It's also increasing. And so as you raise the pressure, the chemical potential in the water goes up. The chemical, and that's according to the molar volume of water. The chemical potential in the membrane also goes up, but according to the partial molar volume, and to the extent that there's a difference between the molar volume and the partial molar volume of water, this can create a chemical potential difference right at that membrane interface. And that chemical potential difference is relaxed by having the concentration of water in the membrane change. That's how you get back to chemical potential equilibrium. If the molar volume of water and the partial molar volume of water in the membrane are essentially the same, then as the pressure goes up, you raise the chemical potential of water in both phases identically, and then there's no change in concentration of water with pressure. And you can kind of guess what the answer is based on the data we've already seen, right? All right. We'll just skip to the end of this, and that is that the concentration of water, which is given by this activity term in the membrane, depends on the difference between the molar volume and partial molar volume of water times the pressure. And so if the molar volume of the solvent, or water, is greater than its partial molar volume in the polymer, then as the pressure increases, the water activity, that is the water concentration, will increase a little bit. Remember that example with the neoprene and chlorobenzene? If the molar volume of pure water is less than the partial molar volume, then as you run the pressure up, the concentration, the activity of water, and therefore the concentration of water will decrease a little bit. And it turns out that these values for molar volume and partial molar volume of water are so close to one another that as you increase pressure here, you see almost no change in concentration. And that's simply because the molar volume and partial molar volume of the water are essentially equal to one another. That's also the reason why the concentration of organic solvent in this material is about equal to its, at 400 pounds, is about equal to its concentration if you just dissolve the solvent, or soak the rubber in cyclohexanone at ambient pressure. So when the partial molar volume of the solvent inside the membrane is about equal to its molar volume in pure liquid, pressure has essentially no effect on the concentration of penetrant that will dissolve in that polymer. Okay. Have a great Thanksgiving, and we'll pick this exciting story up again on the other side.